Hello and welcome to lesson 17 of functions and applications. Today's learning goal is to explain how a, h, and k affect the quadratic function in its graph, specifically when we're looking at the vertex form. So before we start looking at the transformations, we're going to go over some of the vocabulary you need for this lesson. So starting with transform function, so this is pretty much what we call a function when the shape or the position has changed in comparison to the original parent function. For example, when we're looking at quadratics, our parent function is the x squared, so f of x is equal to x squared. So any transformation to that graph is going to be the transform function of the quadratic. So now, how can graphs be transformed? And if you remember last lesson, we did look at translating vertical stretch and compression, reflections, as well as rotations. So with functions, I hope you've seen that we don't really use rotations, but we do have translation, compressions, and stretches, which are dilations, as well as reflections. So starting with horizontal reflection, this is when we are moving our graph up or down or left and right. So horizontal is going to be our left and right movement as well as vertical is going to be our up and down. So when you move right or left, you're changing the value of the x values. And when you're moving up or down, you're changing the y values. So this will be reflected in the mapping of the points. So for example, a point 3, 2, moving 2 to the right is going to now be 5, 2. And if it moves 2 up, then it's going to be 3, 4. Now, a vertical stretch and compression happens when you take your function and you multiply the output by a specific scale factor. So whether that scale factor, what that scale factor is, will determine if it's a stretch or a compression. So if we have that our scale factor is between 0 and 1, then your output values are actually now going to be decreased in comparison to the parent function. And so in doing so, you are taking your original function and you're squishing it down so that the y values are now spread out. And so if our scale factor is a, we will write that a vertical compression is when a is between 0 and 1. And it's not inclusive. And for why it's not inclusive, consider when a is 0. When you multiply it by 0, then all your values are now 0. So your output is just the function y equals 0. And when it is 1, then you're not changing the output values. They're going to stay the same. So it's just the same function. So it's not a transformed function. So when we have a between 0 and 1, we have a vertical compression. And again, think of your shape as being squished down or compressed down. And we can also have our scale factor be greater than 1, which is going to give us that vertical stretch. And in this case, when a is greater than 1, your output values are now increasing. So now think of your graph, you're stretching it up, and now it's more narrow. So if we have this as our starting function, if you, and let me make this blue just to see the comparison, a stretch would make your function more narrow, while a compression is going to make it more wide. And now we are going to look at two types of reflection, which is vertical and horizontal. We are mainly going to be working with vertical reflections, but I will also explain horizontal reflection as well, so we can have a comparison. So a vertical reflection is our most common reflection, and it's pretty much a reflection in the x-axis. And consider a parabola that's this looks like this. If you reflected in the x-axis or vertically reflected, you now have the transformed function as the pink function. And you can see that the direction of the opening has changed in this case. And this is also if a is, this happens when a is below 0. So when a is negative, we know that we have a vertical reflection. And we also have to consider the vertical stretch and compression in that case as well. So with A, we're looking at two things. Is it a stretch or a compression? And if it's a reflection. And consider for the cases when A is less than 0, then if we have -1, uh, A, and then 0. So if A is between 0 and -1, then we have that compression here and a reflection. And when A is less than -1, then we have a vertical reflection as well as a vertical stretch. And it'll just be in the opposite direction of the parent function. And now we also can look at a horizontal reflection. Again, you're not going to really see this a lot, but we can also reflect. I'm going to look at that same black function that I had. And if I reflect this in the y-axis, something like that, then I can see that my direction of opening has not changed, but now my input values are going to be different. So in the vertical reflection, you have that your output values are different, but the x value has not changed. However, in the blue function, which is the horizontal reflection, since you're reflecting in the y-axis, all of your x values are now going to be negative, and the output values are going to remain the same here. So, just to give you a little bit of context now, we're going to look at something that is called our mapping rule. So our mapping rule pretty much tells us if we start with x and y in our parent function, which are going to be our starting or key coordinates, uh, a mapping rule tells us how these coordinates have changed with the transformations that have been applied. For example, if we move a function 4 units to the right, then we can write the mapping rule as xy. So again, we start with xy. This is now, we have to have that arrow to say what it's changing into. Our input values, because we moved 4 units to the right, are now x plus 4. But our output value has not changed, so it remains as y. Consider a function that's translated 7 units down. Now, in this case, our x value is actually staying the same. It's constant because we are not translating horizontally, but we have a vertical translation. So that gives us y minus 7. And if it was a vertical translation upward, we would just have a positive. And same with up here, if it was a horizontal translation to the left, then we have a subtraction. For vertical stretch and compression, which is our next point, we have that scale factor of A. And recall this is always going to be in our output value. So our input is not going to change, but our output value is going to change. And that is what is going to cause our function to become more narrow or wide. And finally, for vertical reflection, we have x of y. And remember, our output values are changing, so this is going to be -y. And I want you to think now, what do you think the mapping rule for a horizontal reflection would be? So for a horizontal reflection, remember that we are now changing the x values. So we have -x and y. And that will be the difference there. And if you have multiple transformations, so a mix of translating compressions and stretches as well as reflections, these can be shown together as well. You will just have a mixed mapping rule. For example, if we combine these first 2 points, so you are translating 4 units to the right and 7 units to the 7 units down, then our mapping rule xy, try to keep it in the same line. I'm just writing this for space, but we'll have x plus 4 and y minus 7. And as well, if you have the scale factors and the vertical reflections, that will be represented there as well. Now, I already mentioned this, but key points is our new vocabulary on this page, and that's pretty much the points that define the general shape of the function. And typically that starts with our vertex for the quadratic and some of the nearby points. So the vertex of the parent function is our 0, 0 point. So we definitely want that in there. And I'll just fill that there. And then we typically choose integer values to make it a little more simple and work with friendly numbers. So here we'll have 149 as well as 149. And we're asked to sketch the graph of this new function m of x, where there has been some transformations taken place. So writing this in vertex form, and it actually is already in vertex form, but I just wrote it a little bit differently so you can visualize it with that a, h, and k values. So here we have our a value, which is our scale factor. We have h here, which is just 0, and we have k as plus 2. So here we are, we have no horizontal translation. We have a vertical translation 2 units up, as well as a vertical compression by scale factor of 1/3. So in applying these transformations, our vertex changes from 0, 0. And if you remember from just working with vertex form, you should know that this is equal to 0, 2. And I want you to think why the scale factor here does not really apply. And for that, you have to consider that here, when x is 0, this whole thing is 0, so the scale factor doesn't make a difference. So we are only looking at that 2 output value, and that's why in vertical stretches and compressions, your vertex does not actually change in its value. It's only when you are translating up and down and left and right that your vertex actually changes. As well as when you are reflecting, because you reflect over the x-axis, your vertex will also change with respect to the x-axis. And our axis of symmetry is actually going to stay at x is 0. And the reason for that is that we don't have any horizontal translations. We have not moved our function left or right, so our axis of symmetry is still the same. And the shape of the graph is, in this case, remember, A is 1/3, and so 1/3 is between 0 and 1. So we have a compression, so it is wider. Or what would we write it here? Wider than the parent function. And here I just wanted to show you these two functions in comparison. So with the red, we have our parent function, and you can see the vertex is at 0, 0. And here we have our transformed function. So the vertex has moved 2 units up because we have a vertical translation 2 units up. And the shape of our parabola, the new parabola, or for the parabola of the transformed function, is now wider than the parent function. And the axis of symmetry is the same. So all the information we had on our handout matches what we see in the graph. And again, you can always use Desmos to double check, especially with transformations, just to get a visual comprehension. Desmos would be a really good tool to use. And now just putting all of that together, we're going to look at transformation of quadratic functions. So this page in particular is very helpful, and keep it as like a cheat sheet for transformations of quadratic functions because it explains everything, and especially it explains a, h, and k and their roles with respect to transformations. So recall we have our transform function, the same definition. So when the shape or position changes, then we have a transform function. And a horizontal translation, so we're looking at this top image here, we can see that when h is 0, so that's just no translation, we have our function in the same spot. But if h is greater than 0, we're translating to the right, and if h is below 0, we're translating to the left. Down here we have in the second visual, we have our vertical translation. So when k is greater than 0, we are moving up, and when k is less than 0, we're moving down, and when k is just equal to 0, we're not translating up or down, so it stays in the same place. Now, vertical stretch and compression, we're going to be looking at the third diagram there, which specifically looks at A. So this is what we were just talking about, when A is below between 0 and 1, you have that it is now more narrow or it's a vertical stretch. So you're taking your graph and you're stretching it upwards. And when A is greater than 1, we have that that it's now in this bottom graph, we see that it is more wider. Here it's also showing the vertical reflection in here as well. So you see that A is less than 1, or sorry, less than -1, which shows that reflection. And so again, all these visuals as well as the definitions are really helpful when considering all the transformations, not just to the quadratic, but it can help you for other functions as well, but this one specifically, especially the diagrams, really help you for the quadratic functions. And that's the end of our lesson today, so not too long of a lesson, but there's some practice now to practice combinations of transformations and how they affect the parent function of the quadratic. And as well, you can practice identifying transformations based on just the graph. So starting with the graph, and then you tell us how it has changed. So take a look at all of those. And as always, if you have any questions, please don't hesitate to reach out, and I'll see you all next class.